Example 4 is a application problem. An open box is to be made from a square piece of material 24 inches on a side. This is to be done by cutting equal squares from the corners and folding along the dashed lines. So this entire side is 24 inches. The corners that we're cutting out are of dimension X. So the inside portion of the box is 24 minus 2x. And the same, since it's a square, we have the same reasoning on the vertical sides as well. So we are to write a polynomial function v of x that represents the volume of the box. Well, down here we have a picture of the box folded up, and volume is equal to length times width times height. So volume is going to be equal to the length, which is 24 minus 2x, times the width, which is 24 minus 2x, times the height, which is this little piece right here. To write it a little bit more nicely, the volume is equal to x times 24 minus 2x, quantity squared. Now just notice that if I multiplied all this out, I'd end up with an x cubed. Okay, so this is going to be a third degree polynomial. So the end behavior is going to be going in opposite directions because that's what odd polynomials do. Now we need to determine our range and our domain for this function. So let's talk about that. The domain would be the x values that would work inside this function that would give us a volume greater than 0. And our range would be the y values, or the volumes that we would get from this function. So taking a look at the domain, I'm going to go ahead and include 0, even though a volume of 0 is meaningless to us here. But as we look at this, if I put a 0 in here, I get a volume of 0. And then if I put a 12 in for x, I once again get a volume of 0. So our domain would be all of the x values between 0 and 12. Our range would be all of the volumes you could get out of that. So our range would of course start at 0 if you had a volume of 0. If I put a 0 here, I have a volume of 0. If I put a 12, I get a volume of 0. And then let's just say what our range would be here, what our possible range could be, if we took x to be as small as possible to give us a large number in here, and then if we took x to be as large as possible, that would give us a large number out here, and a non-zero answer inside the parentheses. Now the thing is, what I just described is the analytical way of trying to find the range. But we don't have all the tools we need to analytically find it for this guy, because we're getting as small as possible, but the volume still exists, and then as large as possible, but the volume still exists within our bounds. The best way to find the range for this particular problem would be to go into y equals, enter the function, and take a look at what's happening between the x values of 0 and 12. So let me get this guy entered. And I'm going to start off, you can hit graph if you want to, but the last problem I did, I had changed my window and I had not set it back to basic. So what I'm going to start off with is going to zoom and hitting number 6, take it back to standard, and it looks very strange, which is okay. I agree. It looks strange. So let's now go into our window and start setting this guy up. Our x values for this function are between 0 and 12. So let's just set it a little to the left of 0 and a little to the right of 12 for our x values. And then our y's right now, we're trying to figure it out. I'm going to set my y value at 0 because that's the smallest volume we can have. If you wanted to, you could set it just a little bit below 0 so you can see the axis showing up on the screen. My y max, I would think at the very least would be 1,000. It might be 15,000. It might be 1,500. Would probably be a more accurate guess. Just choose something. I'm going to go with 1,500, and I'm just going to see what it does. And I'm going to hit graph, and look at that. It shows up beautifully right there. So from 0 to 12, right here, we have this guy set up to where we can see the maximum value. So I'm going to go second, calculate maximum, and I'm going to go left and right. And I'm watching those Y values, trying to figure out where they top out at, and I'm going to try to go just to the right of that. Left bound, and I'm going to do the same thing for the right bound, watching those Y values. It goes up to 1,023, 1,023, then it drops. There's my right bound. And then guess somewhere in the middle, and we have it. It maxes out at 1,024. Okay, so that is the maximum value of the volume for this particular box arrangement, and that happens to be the maximum value for our range. So now we've kind of skipped ahead to see. It says use a graphing calculator to estimate the dimensions of the box and maximum volume. Well, we've already found it, and it gave us this window. If you want to set that window up and see what it looks like, you certainly can. But I've already found my maximum happens when x equals 4. My volume is equal to 1,024. What are our units here? Inches. Inches cubed. And we want to estimate the dimensions of the box and maximum volume. So that would mean that the length is 24 minus 2x. So it's 24 minus 8. 2 times 4 is 8. And 24 minus 8 is going to be 16 inches. The width is the same. And x is equal to the height. So the dimensions will be 16 by 16 by 4 inches. That will give us the maximum volume for that box.